morning friends. Today we are going to discuss a new chapter in this particular subject, mechanics of solids, that is the bending stresses in beams. So in the previous chapter or in the previous session we learnt about types of supports and types of beams. Then we learnt about the types of loads acting on the beam, determination of support reaction by using the equilibrium conditions, that is sigma h, sigma v and sigma m is equal to 0, plotting of shear force and bending moment diagram of statically determinate beam, specifically simply supported beam, cantilever beam and overhanging beam. So all these things we have discussed in the previous session. So today's session, the main objective is to understand the pure bending, understand the concept of moment of resistance and section modulus, describe the behavior of beams under lateral loads, derive the bending equation and discuss the significance of assumptions made in the deriving the equation, and draw the bending stress distribution diagram and calculate maximum normal stress in a given particular beam. So these are the objectives of this particular chapter. So today we are going to understand first session about what is the bending stress. If we take any section of a beam and consider the free body diagram on either side, we find that there must be the three internal stress resultant at the section in general to maintain the equilibrium of free body. So what are those three internal stress resultant? That is the horizontal component, vertical component and moment. These internal stress resultants are equal and opposite to the external effects of loads on the section, that is bending moment, shear force and axial force. So in this particular topic we are discussing the effect of bending, and what will be the effect of bending moment in a particular beam, that we are going to discuss right now. Refer this particular figure. A beam subjected to the external loading, and if we are going to take a section over here, section XX, then at section XX if we are going to take a left part of a beam, so at a section three internal forces are developed, named called horizontal force, vertical force and moment. What will be the effect of moment, that we are going to discuss right now. Under the effect of lateral loads, the beam bends and longitudinal axes take curved shape. The beam produces an internal resisting couple to balance the bending moment due to applied loads. This couple generated by the normal compressive and tensile forces in the section. So if you are referring this previous figure, then refer this figure. Because of this external lateral load, my beam goes bend, and because of this bending moment is developed. This bending moment will be generated, the couple, this couple form, equal and opposite forces. Couple is nothing but the equal and opposite forces. See, this is the compressive force, this T is the tensile force, and this force generate the stresses at the section of a beam named called bending stress. So the beam bend due to the effect of external loads and take a curved shape. Hence, the stresses produced due to bending moment is called bending stress. In the case of a positive or sagging bending moment, the beam concave upward. This bending results in compression in the top fibers of the beam, which shorten in length, and tension in the bottom fibers. These stresses are known as bending stresses. Let us be understood using this tabletop. So if you are referring this, a beam is there subjected to the external loading, any kind of external loading, it will be bent like this. So this is the case of simply supported beam. In case of simply supported beam, for any kind of the loading, the nature of bending moment diagram is of sagging, and we are taking sagging as a positive bending moment. Now here, if you are referring, then the top fibers will be shortened and the bottom fibers will be elongated, means the top fiber subjected to the compression and this bottom fiber is under tension. This generated the stresses at a particular section is known as bending stress. So if we come to the PPT, so the same thing will be explained over here. For a beam subjected to the sagging bending moment, beam concave upwards. This bending results in compression in the top fibers of the beam, which shorten in length, and tension in the bottom fibers. These stresses are known as bending stress. So the same thing will be explained over here. Now let us be understood the concept of pure bending. What is the meaning of pure bending, which has been discussed in the previous session for 2 minutes. Now, pure bending is the deformation of the beam under a constant bending moment. Therefore, pure bending occurs only in the region of a beam where the shear force is 0, because V is equal to dm by dx. It is very much important. Please refer this particular figure. Given beam is a simply supported beam subjected to the 2-point load and equidistance from the support. Because of this is the shear force diagram, and in the central region the shear force is 0. And if you are observing the bending moment diagram, at this region constant bending moment is there, shear force is also 0 in this region, means this is known as the zone of pure bending, and the bending stresses which are generated at this section is to be called the stresses under pure bending. Now let us study today the theory of pure bending. What is the theory of pure bending? What is the concept of pure bending? That is we are going to discuss right now. Let us we are going for certain assumptions which will be used in this particular theory. The first assumption: section which are plane before bending remain plane after bending also. It means that the cross section of the beam rotates about a line, remains plane after deformation. The second assumption is the material is homogeneous and isotropic and also obeys the Hooke's law. Question may arise, what is the meaning of isotropic? Isotropic means material has the same elastic properties in all the direction at a point. Homogeneous material means material has the same elastic properties throughout the body, means the same throughout the material is used. That is, material is made up of same material throughout. The material obeys the Hooke's law, which means that the stresses are directly proportional to the strain. This leads to further the assumption that the stresses are proportional to the elastic limit. I wish you have understood these assumptions very well. The third assumption which has been used in the theory of pure bending is the modulus of elasticity of the material is the same in tension and compression. This means that stress diagram is linear and consisting of two rectangles, specifically triangles. So I will repeat this assumption. The modulus of elasticity of material is same in tension and compression. That means that the stress diagram is linear and consisting of two triangles. We will discuss much more when we are going to plot the bending stress diagram. If you want to understood clearly, please come on the tabletop. If I will take a section on this beam, this is not to scale figure precisely, this is the cross section of a beam. If this is the L is the length of beam, then this will be the breadth and this will be the depth of section. If this will be the neutral axis and the top layer is under compression, bottom layer is under tension, then this is my stress, compressive stress, this is my tensile stress, which has been joined by linear relationship, and we got the two different triangles. This is compression, this is tension. This is the meaning of this third assumption. How to plot this diagram, how to obtain these values, that we will understood in the next session also. Now let us we go to our assumption number 4. The beam is initially straight and all the longitudinal filaments bent into circular arcs with a common center of curvature. This means that a beam of constant cross section, that is a prismatic beam, means if we are referring over here on this tabletop, this assumption says this: a beam must be a prismatic beam, means EI is constant throughout. What does it mean? EI is constant throughout. I is nothing but moment of inertia. E is nothing but modulus of elasticity. Means the modulus of elasticity of the materials is constant, means the material is homogeneous, that is known with us, but our section cannot change like this. This is not possible as per this assumption is concerned, means this is to be called prismatic beam. Okay, let us go to the PPT. Fifth assumption: each layer of the material is free to expand or contract under stress independently of the layer above or below it. This is necessary to ensure that we are able to calculate the stress at any layer using elastic properties. Sixth assumption: the radius of curvature is large compared with dimension of the cross section. So this are the 6 of the assumptions which has been used in case of theory of simple bending. Now let us be understood the basic concept over here. Let us refer a figure first. A part of the beam has been shown over here. This figure shows before bending and this figure shows after bending. Means after the application of force, this is the figure which can be observed and this is the figure which can be observed before bending. Now a part of a beam subjected to simple bending as shown in figure number 1 that we have shown. Consider a small length delta x of this part of a beam. Considering the two section AB and CD which are normal to the axis of beam and N, refer the figure. Consider the two section AB and CD of a particular beam part having a length of delta x. Due to the application of action of bending moment, the part of the length delta x will be deformed. Yes, we have seen the figure number 2, and that from figure it is clear that all the layers of the beam which are originally of the same length do not remain of the same length. If you are referring this figure, just observe this length is delta x, but this is to be shortened. This layer is shortened and this layer is elongated. So if you are going from bottom to top, this elongation is reduced and from the top the shortening of the layers is reduced. So the top layer AC has deformed to the shape A dash C dash and this layer has been shortened in its length, while the bottom layer BD has deformed to the shape B dash D dash and this layer has been elongated. Hence from that figure